parameter. Hello.
Yes, Venice.
Yes,
I
please.
got that.
So we all got this coefficient. Okay, so I'll be explaining the Haussmann test when we get to sigma convergence. Okay, so one thing is that for panel data estimations, there are different models that you can use. And each model was developed to solve a particular problem. So for instance, we have the panel corrected standard error model, which controls for heteroscedasticity. And then the fixed effect model controls for time invariant effects. Okay, so all these models were developed to solve a particular problem. So for instance, the fractional system GMM solved the problem of endogeneity. So as I said, as we move forward, I'll explain the fixed effect model and then the random effect model into details and why we chose the fixed effect model. So when you take a look at the Haussmann test, we said that we choose the fixed effect model when the p-value of the Haussmann test is less than alpha. So alpha here is our level of significance. So I want to show the results. I'll be changing the screen, and then I'll show the results. Okay. No, this is for okay. So can we all see the screen? So I'm scrolling down to our Haussmann test.
Yes.
Okay, so when we perform our Haussmann test, so this is what we are interested in. The data is quite good. Nothing to okay, this is 50%. Haussmann test. Okay, so can we see the probability of the Haussmann test?
Yes, Venice. 0.0.
The probability of the, or the p-value, the probability of the Haussmann test was 0.00. Okay, so that's the probability of the Haussmann test. So based on, now the Haussmann test, is a hypothesis testing. Okay, it's a hypothesis test. And the null hypothesis of the Haussmann test says that the random effects, okay, the random effects of the independent variables 2. So the Horstman test, the null hypothesis of the Horstman test says that the random effects are independent of the predictor variable. So I said I'll explain it in when we get to sigma convergence. Okay, so after running the test, we had a p-value of 0, and we reject the p-value when, well, we reject the null hypothesis when the p-value is less than the level of significance. So here we see that our p-value of 0, if you look into your results, you see that your p-value for the Horstman test was 0.00. Okay, so here I chose one, it can be 5% level of significance. However, our p-value here is not up to even 1, it is 0. So I chose my level of significance to be 1%. But let's assume that your p-value was 0.01. 0.01 is still significant. So you can say that your p-value, your results is significant at 5% level of significance. All right, are we okay? So when we look at the next slide, we said that so fixed effect model is preferred when the p-value is less than alpha. So we chose alpha to be 0. Alpha can be 0.05, it can be 0.01. But here, because our p-value was less, I chose alpha to be 1%. So because our p-value is less than 1%, which is our level of significance, we chose the fixed effect model. So after we chose the fixed effect model, we went further to estimate the fixed effect model using our robust test to correct for certain biases in our estimate. All right, so after that, we got a coefficient for the robust test, which was negative 1.21. So we said that there is presence of beta convergence when the beta parameter, the coefficient of our beta parameter is less than 0, which means that the coefficient of our beta parameter is negative. So we said that the coefficient of the beta parameter estimated was negative 1.21, indicating the presence of beta convergence within the Ghanaian insurance sector. Now, the implication of this is that, now last week, Doc made some changes. We said that we were using inefficient firms. We said that beta parameter measures the tendency by which inefficient firms converge towards the best practice frontier. However, we were corrected with that statement because now we are not dealing with just inefficient firms. Doc made us understand that there are banks which are inefficient, yet they have, or he made us understand that we are not only considering inefficient firms, we are considering all firms. So it's right we use the word average. So we use beta parameter to measure the ability of average efficiency firms to converge towards the best practice frontier. So we said that the implication of this is that the average efficient insurance firms are moving at a speed of 121% towards the best practice frontier or towards the efficient frontier. So this is how we estimate our beta parameter. Any question? Any question?
Any question?
Hello, Dennis.
Yes.
Dennis.
Yes.
Please, can you please show me your data output file again? I think I saw a p-value of -0. I don't know if I'm mistaken.
Okay.
If you can show me the data output file. Yes. You see the p-value is -0.
Yes.
I am getting a p-value -0. I think there's something wrong with your data. You can't make your conclusions based on that. I think we have to be very careful. We have to check your data. We have to check your model as well.
Okay.
So if maybe you can go back and check the computation. I don't know, because having a negative p-value and especially -0, I don't think you've seen something like -0 before. If it's 0, it's 0.
A minute, please.
I mean, if it's 0, it's 0.
Yeah.
I don't think there's anything like -0. So I think please we should go back, check our computation, check the data as well. Because maybe this could be driven by certain outliers. Please, did you address the outliers?
No.
Yes, so I think, hello?
Yeah, I'm here.
Yeah, so please, I think we have to check the outliers and correct these outliers. So maybe it could be that there are some extreme outliers that is making you get something like this.
Okay. Okay. All right, then we'll check that. Now I want to be sure I shared the right file.
Okay, okay, okay.
Okay. So I think this is rather. Okay, so I'll check. Okay, Hilda, I'll check the data set again.
So please, you have to check maybe your summary stats. Your summary stats at least will let you have an overview of whatever the possible outlier that you may have. Because I know you use the cost efficiency and all that. So just create a summary stat for the cost efficiency and see the possible outliers in it. So to correct for that, you can rasterize it. You rasterizing it, you wouldn't lose data, but if you decide to cut them off, you are going to lose data. So please check your data first and let's see. Okay.
Okay, thank you.
Thank you.
Okay. But please, can we check our results to see? Dinah,
Yes, Venice.
yeah, can you check your results?
For the p-value,
Yes.
I had 0.000.
You have 0.000.
Yes.
Okay, so it could be that maybe I shared the wrong file. I named it
Okay.
because I had 0.
Mine is positive, not negative.
Positive, yeah. So it could be that I shared the wrong file instead. Okay, but do we, apart from Dinah, do we all have 0 instead of -0? Do we all have +0?
Please.
Yes, yes.
Positive 0. Yes, for me.
Okay. So I'm sure maybe it's from the file I shared. Maybe I shared the wrong file. So let's stick to this. So since we all use the same data and we all had a p-value of 0. A p-value of 0, we stick. Okay. So far, are there any questions? Are there any questions? Okay, let's proceed. I'd like everyone to write this model down so that we don't move back and forth. Okay, I'd like us to write it down so that we don't move back and forth. So let me know when you are done. So please write this model quickly so that in explaining the commands, we don't move back and forth to explain each item in the command. So are we done?
Yes.
No, please. No, please.
Okay, are we done? Hello. Hello, can we move on? Okay. All right. So from what we learned in beta convergence, we all know what this symbol here means. It means change. So the change in EIT is a change in the efficiency or productivity score of a firm at time T. The Y hat, we are all familiar with X bar, but here we chose Y hat. So the Y hat here is our mean or the average efficiency score for the industry at a particular time. And then the Y hat T minus 1 is the lag of the average efficiency score, okay, of the industry. So the lag simply means the previous mean of the industry at a particular time. All right. Then the beta, the sigma parameter here is the unknown parameter of interest. That tells us the rate of sigma convergence. So we said that sigma convergence measures the tendency at which all efficiency, if you are doing an efficiency study, or all productivity levels within the industry are converging towards the mean levels within the industry. So you can see from here that we said the unknown parameter of interest indicates the rate of convergence from YIT to Y bar T, which is the mean of the industry. Then the YIT is the efficiency score of firm I at time T. Then the YIT minus 1 is the lag of the efficiency score or the previous efficiency score. So once we've written this model, we said that in testing for beta convergence, these are the steps, okay, the general steps. So you estimate your scores, depending on the scores you are, the efficiency scores you are using or productivity scores you are using. You estimate them using the MaxDA software, then you prepare your data. So I'm sure we all know how to prepare our data. Then when you are done, you use the required codes in STATA to run your test. So we looked at how to prepare our data, and I know we are all conversant with it. So in running the test, these are the steps. So first you have to load your data onto STATA. but I want us to explain the codes and then we run through the steps quickly. So we said that the second step is to prepare STATA to run panel data analysis. And with that, we use this code. So this code will set or will tell STATA that we are coming to run or we are about running a panel data analysis. So when we run this code, STATA is able to tell us our year period and then whether our data is we are using whether we are using a balanced panel data or an unbalanced panel data. So now let's go to the model. Okay, in estimating the model, first we have to generate the log of our efficiency score. So here we are using technical efficiency score. But in your study, if you are using cost efficiency, you use CE. If you are using, so depending on the efficiency score you are using, you change this part. Okay, so given the model, so let's refer to our model. So given the model, we said that change in IT is equal to log into brackets the efficiency score of a firm at time t. So the YIT, we said the YIT, what is the YIT? Who can tell us what the YIT is from what you have written? Hello? Hello? Yes, who can tell us what our YIT is?
Okay, so Benes,
Yeah.
you said the YIT is the efficiency score of a firm in time T. That's the current year.
Okay, the current year. So we are taking the log of that efficiency score. So the efficiency score is the TE, okay, in our data set, and then the log. So it's equal to the natural log of the efficiency score. So we understand that part of the model now, don't we?
Yes,
You
please.
do.
Okay, so we move to the next one. It is minus the natural log of the average. Okay, the average or the mean in time t. So the natural log, so the log of the mean, which is equal to ln into brackets the mean. Do we get this part?
Yes.
Yes,
We
please.
are just explaining the model using the required codes. We are connecting the model with the codes so that you better understand the codes. Okay, just like we did last week with the beta convergence. So we proceed. Now we generate the lag of TE. So the lag of TE is the previous efficiency score. So given this, so let's move to the next one, the next expansion of the model. We have EIT minus 1, which is equal to ln into brackets the log of the efficiency score. So we are computing the log of the lag of the efficiency score. But before that, we have to find the lag. That is why this code is here. So you generate the lag of the efficiency score. So generating the lag of the efficiency score, this is how we generate the lag. Okay, then when we are done, now I said in the model you have the natural log of the lag. Okay, but before we generate the natural log of the lag, you have to first find the lag. So after finding the lag, now we come here to generate the natural log of the lag of the efficiency score. So the natural log of the lag of the efficiency score. So do we get this code here in relation
Yes,
to the
please.
model? You understand it now?
Yes,
Yes,
please.
please.
So we proceed. It says that minus the lag of the average. Okay, please, can you all see your model? Can you all see the model you've written?
Yes.
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 So someone should mention the part we've gotten to. Just say it so that we connect it with the code here. So which part are we now? Which part are we now?
Hello, Dennis. Can you please repeat the question? I don't think I really understood it.
So we are trying to explain the codes. Okay, we are trying to connect the codes with the model to explain which components of the model we are calculating. All right, so we looked at the log of the lag of the efficiency score. So when you copy, if you copy the model rightly, you see that we have EIT minus 1 is equal to the natural log of the lag efficiency score minus ln y bar t minus 1. All right, so we've already explained the first part. So I want to know which part we've gotten to. If you are following, I'd like to know which part we are yet to explain.
We are gen lag, we are the gen lag mean is equal to mean underscore n minus 1. So we've now developed the value for y bar t minus 1. So then the next code we do will be for the log of it.
Okay, so exactly. So the formula says that, or the formula here says that the log of the lag of the average of the mean. But we have to find the lag of the mean first before we come to find the log. So as you said, you rightly said it. So this is the lag of the mean. Then we generate the log of the lag, the natural log of the lag mean. So we proceed to the next step. Now it says that the EIT, so after calculating each component, we come and then we generate the changes. So we are generating the change in TE, and the change in TE was given by the natural log. So from the model, right? From the model, please mention the formula for the change in EIT.
So that was EIT minus 1.
No, I want you to give us the model. EIT, EI, comma T.
Yes, minus.
I want you to give us the entire model.
The entire model.
Yes,
okay.
Model, yeah.
Okay, so the entire model was change in EIT is equal to sigma 1 EIT EI minus T minus, sorry, EI comma T minus 1 plus sigma 2 trend T plus UI plus EIT.
Okay. So now what's the, under the, we expanded the change in EIT. So what was the change in EIT from the model? The expansion you have below the model.
So that is change in EIT is equal to EIT minus EIT minus 1.
No, the first part. I'm talking about the entire expansion.
The expansion of the left-hand side of the model, right?
No, after you, I'm referring to this. So you have EIT, or you didn't write this.
Okay, I wrote it.
Did we write this? So I was referring to this. So it's the natural log of the efficiency score minus the natural log of the mean.
Okay.
Okay. So we are calculating the change. Okay. So we said the natural log of the efficiency score minus the natural log of the mean. So that's the meaning of this. Okay. So we are trying to connect the code with the model. Okay. All right. So are we okay?
Yes, please.
Are we okay? So we move to the next part. Okay, I want someone to tell us the model. Okay, the model for the EI or the lag of the efficiency score, which is the EI comma T minus 1.
EI EIT minus 1 is equal to the natural log of YIT minus 1 minus the natural log of the mean of the previous year.
Okay. So given the code, what he just said is the efficiency score minus the log of the lag of the mean. Okay. So given all this calculation, we come and then we estimate our regression. So as you can see, we use lag T1 here. It's because we already have generate lag T here. So we have to separate them. If not, STATA will pick this calculation instead of this. Do we get it? Are we good? So it's all
Yes.
we are generating the TE. Okay, but we already generated lag TE here. This formula, although they are both lag TE, they are slightly different. So we have to differentiate them. Okay, so that STATA will pick the right computation. Right. So after this, our next step is to estimate the regression, because we are done calculating the components of the model. So we have our regression. So this is to generate the regression results for ordinary least squares. So given the regression, this is our dependent variable, which is our change in T, then our dependent variable, then the trend. Okay, so STATA will run the results for us. Then we said that we use outrec2 to save the commands. Okay, outrec2 to save the command. So I want us to take a look at this. Okay. So now when you save your command, your results are saved in Word, but you can view the output here. So you just click on the name you used in saving it. So you can see it opening in Word for you. So can we see it? So instead of using the shell out, when you run the outrec2 command, the outrec2 using your preferred name dot the document, you just come here and click the document, and then STATA will pull out the document in Word for you. So my document has already been opened. So that is it with the command for saving your file in Word document. Okay, so please use your own name, any name you want. Okay, you can use any name you want. Then you add the dot document. All right. So now we went further to estimate the regression. Okay, for fixed effects. Okay, for a fixed effect model. And then we said that the e-store here, FE, helps you to save the data, or to helps STATA to save your results for you, so that it will make it possible for you to run your Horstman test. So each time you are done, if you want to perform a test, you just run your results, and then you use this command so that STATA will save the results for you for further tests. So same applying to the random effect model. Now, if you all looked at your results very well, you realize that after we generated the fixed effect, okay, when the results came, you see that they've written fixed effects within results. So STATA was able to tell us that there was fixed effects within our results, even when we didn't do the Horstman test. So we are doing the Horstman test to confirm that indeed there is a fixed effect within our model. So we'll explain fixed effects and then random effect as we move on. Okay, so after we estimate the random effect, we did that to perform our Horstman test. Okay, to perform our Horstman test. So now, I said that in panel data estimation, there are different models we use, and each model solves a particular problem. Okay, so given the generalized panel data regression, I'll illustrate this. Okay, so given the generalized panel data regression, so you have YIT, which is the dependent variable, equals so this is our intercept, then plus our independent variable. So we have lots of independent variables, and then the beta is the coefficient of our independent variable. Okay, so this is the independence, the beta parameter of our independent variable. Okay, so okay, so this is the generalized panel data, a generalized model for a panel data regression. Okay, so each regression, when you are estimating a particular regression, some of these variables will be missing. Okay, you won't include some of these variables, especially the UI, the lambda t, these two. Okay, so each model has their unique characteristics, but this is the generalized panel data model. So now you all know that this is your dependent variable, this is your intercept, this is the beta parameter of all your all your independent variables. Then we call this the composed error term. Okay, the error term. Now the real so it's the composed error term. Okay, it's your error term. However, the error term is splitted. Okay, it's made up of the individual specific effects, then the time specific effect, and then the stochastic term or the random noise. So I said that the last time, I said that your error term consists of, now when you are doing or when you are estimating a regression model, you can you have your independent variables you are looking at. And there are so many independent variables. You can't look at every independent variable in your study. So the other independent variables you are not looking at, which have effect on this dependent variable, yet you are not studying them as an independent variable. All those variables are in your error term. Okay, so that is what the error term is. Now the error term is made up of these factors. So I said the individual specific effect, the time specific effect, then the error term itself. All right. So now with the fixed effect model, so in estimating using your regression results using the fixed effect model, there are certain assumptions. Okay, there are certain assumptions that must hold. And one of the assumptions is that the UIT here, which is our individual specific effect, has a correlation with our explanatory variable here. So they correlate. So there's a correlation. Okay, there's a correlation with the independent variables here, or the explanatory variables. Okay, so there's a correlation. However, when the assumption under random effects, okay, is saying that these independent variables are not correlated with the individual specific effects here. So that is the assumption. This says that this is correlated with this, and then this is saying that they are not correlated. Your independent variables are independent. They have no association with the individual specific effects. So who can tell me what the individual specific effects are? We've all done a bit of regression. So who can tell us what the individual specific effects are?
Hello, Benis.
Yes.
Please, point of correction. The individual specific effects should be UI, not UIT. Yes, it should be UI, not UIT.
Okay.
Thank you.
Okay. So UI. Thank you, Hilda. Okay. So you. Okay. So who can tell us what are individual specific effects are? Anybody? Hello, anybody tell us?
Yeah, Dennis, factors that affect, specific factors that affect the industry being studied.
All right, you've tried. Anyone else?
Please, your question again.
So I was asking what the individual specific effects are.
Hello, size. Size.
Okay, so size is one, but I want to, okay, so the
no. Hello.
Yeah,
please,
hello.
The individual specific effect here means that something that does not change across time. Size do change across time.
Yes.
So if something, the UI means that something that does not change across time. So let's take something like gender, for instance, not in relation to this insurance industry. We take something like gender. Does your gender change across time? No. Please, do you get it?
Yes, please.
Yeah.
Yes.
So individual.
So it should be some. So the individual.
Yeah, so the individual specific effects are also variables, okay? Variables that affect the industry, or they are the characteristics that affect the industry you are understudying. The entities you are understudying. So let's say that for the banking industry, okay, what are some of the characteristics that affect the banks in the industry? Those factors are the individual specific effects that do not change over time. Okay, so for instance, in the banking industry, we have ownership. So you realize that over time, if a bank is domestic, it is domestic. Okay. Or if a bank is foreign, over time, it is foreign throughout. All right, so for instance, HFC Bank was domestic from the time it was incorporated. However, it became foreign in 2015. Okay, so ownership in the banking and ownership also applies to the insurance sector. So individual specific effects in the insurance sector, we have ownership to be fact. So we said the individual specific effects are effects, okay, are characteristics that affect the entity you are studying, or that are peculiar to the entity you are studying. And those effects do not change over time. They are time invariant. They are constant over time. Are we okay? So those are the individual specific effects. So within the fixed effect model, the assumption is saying that this individual specific effects correlates with the explanatory variables of interest, which you are using in your study. So when we use the fixed effect model, what it does is that it controls for this time-specific effect so that we come out with coefficients that are free of biases. Are we okay? So that coefficients will reflect um, the actual results we are trying to come out with. So let's assume that we don't test for the model to use, and we go and use random effect. If you look through your results, you realize that the coefficient we got from random effect is different from the coefficient we got from fixed effect. So let's assume we don't test and we use fixed random effects for our conclusion. You realize that we'll come out with estimates that are full of biases and they are inconsistent with the actual convergence within the industry. So it is right that you apply the correct model. Okay. So for other models, most of the times we run certain tests. Okay. For instance, if you want to use let's say um, uh, the panel corrected standard error model. We said that it accounts for heteroscedasticity, or it solves the problem of heteroscedasticity. So you can run a test, giving your data set to know if you have, or if your data set is heteroscedastic. Then if it is, then you can justify why you are using the panel corrected standard error model. Are we okay? So in summary, all regression, there are different ways of estimating panel data regression, and each model solves a problem. Okay, so the fixed effect model controls for the time invariant effect or the individual specific effect that are constant and do not change over time, so that when we come out with our coefficients, they will be statistically significant and they will be devoid of biases. Okay, so the Horstman test is just a test that allows us to test which of these models we should apply. Okay, which of these models we should apply, given our data set, which of these models we should apply. So when we perform the Horstman test, so like I said, the null hypothesis, okay, the null hypothesis of the Horstman test says that your independent variables do not correlate with the the individual specific effects. Okay, and then the alternative hypothesis says that it correlates. Okay, so the random effects are independent. Okay, there's no correlation between the UIT and your explanatory variable. Okay, whereas the alternate is the opposite. All right. So when you estimate your Horstman test and the probability value. So let's go to, so as we are studying sigma convergence, okay, so this is the results, right? Can you see the STATA output? Can we see the STATA output?
Yes, Vanessa, but it's very
Yes, please.
small. Maybe you can enlarge it small.
Okay.
Thank you.
I'm unable to enlarge it.
Okay, Vanessa, we can go on.
But we can see it, right? Can you see the,
Yes.
so this is what we are interested in. So this is the p-value of our Hotman test. So 0.000. Are we okay? So with this
Yes.
p-value, we can boldly reject our null hypothesis. Okay, that the null hypothesis, we say that the random effects are independent, meaning that they are not independent. They correlate with the individual specific effect. So this is a proof that our fixed effect model must apply, because the assumptions under the one of the assumptions for the fixed effect model is that the individual specific effect correlates with the explanatory variable. So we said that fixed effect model is preferred when the p-value is less than your chosen alpha. So here our alpha was 1%. Okay, so we rejected our null hypothesis, okay, based on our Hotman test, which tells us that so which told us that our p-value, which is 0. Our p-value, which is 0.01. So at 5% level of significance, okay, the p-value was 0. Let me check. Okay, so our p-value was 0.00. So our p-value was 0. Okay, so I'm changing this to okay, so our p-value. Please, which screen can you see?
The slides, please.
You can see the slide.
Yes. Okay, so our p-value was 0.
at 1% level of significance. So we rejected our null hypothesis, and then we chose the fixed effect model over the random effect model. So we went further to estimate the robust fixed effect model. Okay, and from the results, we realized that the coefficient of our sigma parameter was negative 0.18. Okay, our coefficient was negative 0.18. Did we all get that?
Yes, I got
Yes,
it.
please.
We all did. Please, how many of us got this coefficient? Please raise up your hands. How many of us had negative 0.18? Okay, 6, 7. So please, if you didn't run the test, kindly do so. Okay, after today's lesson, kindly pick the slides and then run the codes with your data. Okay, so far 8 of us have this result. Okay, so from the explanation we gave to beta, the coefficient of our beta parameter, I'd like one of you to interpret the coefficient for sigma convergence. So who is interpreting the coefficient for sigma convergence? Who will help us with the interpretation? And who is helping us with the interpretation?
Benis.
Yeah.
So the coefficient of negative 0.18 indicates that the productivity levels of firms in the insurance industry is moving towards the average level at a rate of 18%.
Please come again.
So I said that the coefficient of negative 0.18 indicates that the productivity levels, efficiency levels of firms in the insurance industry is moving towards the average. It's moving towards the average efficiency level at a rate of 18%.
Okay, but I think you left something on the average efficiency level of the industry.
The industry, sorry, the industry.
Okay.
Thank you.
So please, did we all get his interpretation? Okay, so we said that it implies that the efficient insurance firms are moving at a speed of 18% towards the average efficiency level within the insurance industry. So we all know that when the coefficient is less than 0, there's presence of convergence. Okay, so that is how you interpret your coefficient. All right, and then I think last but not the least, I want to draw our attention to the results on STATA. Okay, so so in your estimations or in your output, okay, you need, this is what you would have. Okay, so this in okay, I think I should have explained. Let me quickly quickly move here and then explain this. Okay, so if you realize we saved the results for the ordinary least squares, okay, then when we got to the robust, after we ran the robust test, we said outwork using the preferred name dot the document. Now we included the command append. So append means that you want STATA to include this result, okay, this fixed effect result to the other document you saved. So you want STATA to include it to the other Word document or the first document you saved. All right. If you want STATA to change the content of that document, you just write replace. Okay. Replace means that STATA should clear the first results and then put in or fix in the new results you're about to enter. So append means you want STATA to include it. So I just said this to draw our minds to the command to better understand this output. So this model here, you can see this. This is the OLS output. Then this is our robust fixed effect output. So the LATE is what we are interested in. So this is what tells us the rate of our
Convergence.
sigma, yes, sigma convergence. All right. So we move.
Hello,
on.
Bennett.
Yes.
Please, with this Word document, I'm just having the first side. I didn't get the second side.
Okay. Then it means that you didn't save the OLS results, right? What coefficient did you get for the lag TE?
Negative 0.18.
Yes. So it means that you didn't save the first command. You didn't save the first result. Okay. But our focus was not on the OLS estimation. Our focus was on the fixed effects estimation. Okay, so if you wanted to save it, then you could have just saved it with the outwork formula. So outwork command, sorry. So outwork 2 you use your preferred name and then dot document. Okay, then when you get to the fixed effect, all you do is to use the same document name. So you are just adding. So you add append to tell STATA that STATA should add the results to the former document you saved at first. So after you can try that. Okay. So after
Okay.
this lesson, you can try it. Yes. So let's go to this result. So this is what we need. Okay. After we've explained the lag TE, which is the coefficient of our parameter, we need this, the F test. Okay, and then this is the p-value of the F test. So the p-value is significant at what percent? Who can tell us the level of significance for the, who can tell us at what percentage our p-value is significant at? So to 2 decimal places. So the p-value of the F test is significant. This is 0.0089. So who can tell us the level of significance for our p-value, the p-value of our F test?
Bennett is 1%.
Is 1%. Okay. So she's right. It is significant at 1%. So like I said, our F test is of interest to us. So what the F test tells us is that the F test represents the joint significance of our explanatory variables in explaining the differences in efficiency growth for a reliable regression result. Okay, so the F-test is telling us how significant our model is, the joint significance of our model. Then the probability value, which is the p-value, is telling us that the F-test, so the probability value here is for the F-test. So it's telling us that our model is statistically significant. So I said that the F-test tells us the joint significance of our explanatory variables in explaining the variations in efficiency growth for a more reliable regression result. That is what the F-test tells us. And then from here to we can see that our p-value, okay, our p-value for the coefficient, is it significant or is not significant? The p-value for our coefficient, which is our beta parameter, is it significant or is not significant? Please, who will tell us, is it significant or is not significant? Hello? Hello? Hello?
Hi.
Yeah. So is our p-value for the coefficient significant or not significant?
It is.
It is. At
Yeah.
what percent?
1%.
At 1%. Okay, so you are right. So our p-value for the coefficient is statistically significant at 1%. Okay. So are there any further questions? From what you've done so far, are there any further questions?
Dennis,
Yeah.
please, I want to find out the word outputs that you showed us. And in your analysis or in your explanation when you are writing your thesis, is it only the parameter, the coefficients that you will talk about, or you also have to talk about the trend and the other figures over there?
Okay, so mostly from published papers, some discuss everything, some interpret all the results, some just focus on the F-test and then the probability value of the F-test, and then the beta parameter or the sigma parameter. So some studies stop there, others go further to explain the trend and then the constant. Okay.
Okay.
So for the trend, I've read a couple of papers, they've interpreted it, but I was looking for an opportunity to ask them and then to further understand the meaning of the trend and then the constant when it comes to convergence. Okay, so I'm sure Doc is listening, but I have notes from what other studies have said about the trend, their interpretation for the trend, as well as the constant. Okay, so
Okay.
I'm sure Doc will help us to better understand how to interpret the trend and the constant.
Okay, thank you.
So,
Benny's.
yes.
Please, I have a question but for the STATA app. So when you save your file and you exit and you come again and you want to open the file, how do you find the documents? Because when I reopen the file, I find no code, but I find the Excel file at the other side.
Okay. So you have to save the code. Okay, you have to save the code. So the simplest way is to create a do file. Can you see this? Can you see this?
Yes, I can see.
So you create a do file, then you type your codes here. Okay, when you type your codes, you save it. So that the next time, the next time you want to run the test for beta convergence, you don't have to copy and paste. Because when you open it, you just have it open. You just open it as. So can you see the do file? So as
Yes,
you are
please.
running your test, you can just open the do file and then you copy and paste it to run your test. So this is where you save your commands in STATA. So you come here, open the do file, then you type your commands here.
Okay.
For further analysis.
Okay. Thank you.
And it's possible to print your results to have a PDF of your results. Okay, so if let's say you are done with all this analysis, you want to save all this. Okay, you want to save each one in Word, and you have to use, after you run the command for the regression results, the next step is to type the outward command that allows you to save this in Word document. However, if you want to have all this, okay, in PDF, it's possible. So you just go to, can you see the printer here?
Yes, please.
So you just click on it, then you click on results. Okay, you can see Microsoft Print to PDF. Then you go to print. So when you go to print, you just choose a header. So any name. Okay, the name you want to save your file. After clicking, after typing in your preferred name, you click OK. Then you choose the directory where you want to save it. So you can see I've saved a couple of PDFs here. So I can change the name to so once it's done printing, it will save automatically in that folder. So when you go there, you can see the PDF. Okay. So
Yes. Yes.
any question? Any question?
Venice, please,
Yeah.
there's something that I just want to comment on. Like, there's a correction
Okay.
that I just want to make.
Okay.
Can you please show me the fixed effect regression, I think the robust one? You asked a question concerning the significance.
Okay.
And I think I did hear someone say it's 1% or so. Can you please show me that regression model?
Okay.
Not the Word document.
Yeah, the PDF. Sorry.
No, not the PDF, on the STATA.
On the system.
The results window. I want to see the results window.
No, sorry. Oh my goodness. Sorry. I think I closed it.
Because I think you were just showing it. This your STATA.
Yeah.
So I think maybe you have to go down. Yeah, please go down. Yeah. You go down. Yeah, I think the robust. Yeah, leave it here. You see the p-value is 0.012. I think you guys were thinking is 1%. It is not significant at 1%, but at 5%, because this value here is more than 1%. You can even confirm this from your from the Word document, because the Word document, you see the asterisk there. Because I think people are thinking because it's 0.01, it's still 1%. It's not 1%. So this time around, it's significant at 5%.
At 5%. Okay.
Yes, because it's more than 1%.
Okay.
Even if it's 0.011, it's still more than 1%.
More than.
Yes.
So I think so now does it mean that it's best to read from the save file than to convert to 2 decimal places here?
Oh, no, not about you converting, but looking at it. So you reading from here, don't try to convert to maybe 2 decimal places or something. Because even you show me the Word document. Can you please show the Word document?
Okay, it's already open.
It's already open. Can you please show us it?
Yeah, let me show.
Because most of it is the coefficient that they run it off to the nearest decimal point.
Okay.
So if you can show us the Word document, you see the asterisk is 2 star.
Yeah,
the negative 0.1. Yes, showing that it's 5% what? It's significant at 5% level. Do you get it? So immediately, if it's more than 1%, it's more than 1%. So the significance is rather 5%, not 1%.
Okay.
Yes. Thank you very much.
Thank you, Hilda. So please, do we all get that? So you can write this down. When it's 2 star, it's significant at 5%. When it's 1 star, it's significant at 10%. And then when the stars are 3, it's significant at 1%. Okay. So in order not to confuse ourselves, just look at the save Word document and then you check the stars. So you can even see it here, 3 stars, 2 stars, and then 1 star. Are we okay?
Yes, please.
Hilda, please, is there anything you'd like to add?
No. I think you've said it all, so that's fine. Yeah.
Please talk around. Okay. Doc.
All right, so everything is sorted. I want to ask 5 of you something. Akotia, do you understand everything that has been done?
Doc, I understood most of it. I
Yeah.
have to go back in. Yes, sir. Hello?
Do you guys hear me?
Yes, please, I can hear you.
Okay.
Hello?
Edwin Abini, do you understand everything?
Yes, Doc, I understand most, but I have a problem with a few things, but I'll go over it again.
Yes, Doc.
It looks like I can't hear their voices unless it's mine. Let me see something. Dennis, can you hear me?
Yes, Doc, I can hear you.
Oh, no, wait. The keywords to use in Google Scholar to get those 5 papers, aside the ones here, you can use keywords like convergence or efficiency convergence. And then you can add sigma and you can add beta. So you can just type beta convergence, sigma convergence. And then you should always add DEA efficiency. You should always add DEA efficiency because we want the ones that have been done in the world of efficiency. You see, when you get these papers, the advantage is that you will be able to know how they interpreted those scores. How they interpreted will help you to know how you will interpret yours. How the model, you see that some of them, the model is different from ours. And so you need to know why is that the case. And they become part of your references. One of the things you're going to indicate is that you're going to indicate at some point that many of the studies that have been done on maybe banking efficiency studies in Ghana, or maybe insurance efficiency studies in Ghana, or maybe energy efficiency studies in Ghana, or maybe oil efficiency studies in Ghana, they have not considered the convergence of efficiency. They have not examined convergence, and you are doing it. So this is another contribution. Of course, why you are doing convergence, Bernice has explained it to you. So I would like you to all have some papers, especially if you look at the bottom one. I put that one on the group page. Convergence in banking efficiency across European countries. Watch how they estimate those convergences. So that's it.